So basically in practice, even though this is a beautiful theoretical result, you'd probably still use the with no log projections, and they would work probably just fine. Okay. Let's see how much whiteboard we'll need. Okay. So what I'm going to do before we move on to compressing matrices is I'm going to look a little bit at what people use for string kernels. And the motivation for that is that, you know, when people process documents, sometimes you may want to have approximate matches. And so there you then want to look at all sorts of substrings. So for instance, when you're doing motive finding in bioinformatics, that's one of the key things that you care about. There's no trash can. Okay, fine. And when you do this, you can immediately see that this gets super expensive very quickly. More to the point, if I, let's say, have, you know, the 4 different base pairs, so A, C, T, and G, and with the matching ones, then for a string of length L, I have 4 to the L different sequences that I could possibly encounter. Now, it turns out biology is quite kind to us, that you don't really observe all possible such sequences. However, instead, you actually observe only, don't worry, we'll be using both. You observe only a very small subset. So what you can then do is you can start thinking about efficient data structures that will actually store only those relevant terms. There's something called a Cuckoo Hash, and you should talk to Dave Anderson about a very efficient way of dealing with this. I'll now show you also how you can deal with that with hash kernels. Okay, good. Present. Okay, great. Document camera. Okay, so these were. Okay. So remember what we had was a kernel of the form, let's say, k of x and x prime was just the sum over all the i's, x coordinate I times x prime coordinate I. And this then gave us a function f of x, which was basically sum over xi wi. And furthermore, we then transformed this was the hash kernel, into sum over I sigma of I xi w subscript hash of I. Right. So this was basically the initial construction that we used. Right. Now, if, for instance, X was a document, so the document is something like the bag of words, okay, then you would map this into the following sparse vector, the 1, bag 1, of 1, and words 1. Okay, which is probably something you can still do, and then you should probably use something along the lines of TF, IDF for reweighting. Ask your friends in LTI exactly how to do this efficiently, but basically it's something like you weigh it by how frequent it is within a document, and you divide by how frequent it is across all documents. So this is a way of finding out, basically giving discriminative words higher words. Now, But we all know this is kind of boring, right? Because this is not really very order specific. So what you could do is you could also add things to it like the bag, comma 1, and bag of, and then of words, 1, and so these would be all the bigrams. You could add all the 3 grams, and so on. As a matter of fact, if you send a nice email to Google or Yahoo and ask them for the n-gram corpus, they will probably give it to you. Or you can take any other document collection and basically extract the n-grams. And they actually tell you a lot about language. Now, what you can immediately see is if I go from singletons to bigrams to trigrams, the number of distinct coordinates that I get will explode exponentially. It gets even worse if I look at all possible substrings. So, for instance, if I want to make sure that nobody sends me an email where they want to write Carnegie but really aren't really allowed to for whatever reasons, that they might actually replace the I by a 1 and so on and so on. So maybe for Carnegie this is not such a big deal, but for Viagra this is a big deal. And my guess is you've probably seen a lot of emails where Viagra was misspelled in interesting ways to make it through spam filters. Now, you can avoid this by just adding wildcards. So you might just say, well, I make a string match against anything of this form, anything of this form, and so on and so on. And maybe also for substrings. So this blows up the number of possible strings and substrings and features even further, and it's usually a great pain to actually construct a dictionary that would work for this. So some time ago people came up with this idea of what they call a string kernel. And it's not quite clear who all the people are who came up with it. So Christianini, Drucker, Lodi, Shaw-Taylor, Hafner, a lot of those folks essentially suggested very similar ideas. So one variant is basically I have k of x and x prime to be the sum over all substrings in S of x. I'll explain in a moment what I mean by an S of x prime times some coefficient lambda subscript s. Okay, so basically in S counts how many times the substring S occurs in X. Likewise here it counts how many times it occurs in X prime. It then gives it some weight, and presto, here's your kernel. This is something rather popular in bioinformatics, where for instance lambda S might be something like lambda to the S, where lambda is a number less than 1, and S is the length of the string. So basically you give longer strings lower weight. Now if you have base pair sequences of length maybe 150, and you want to look at everything up to length 100, you very quickly see that you're going to run out of memory very fast. And so what you can do is instead you can use the hash kernel to, well, basically first of all you tear this apart, right? So this is the inner product between phi of x and phi of x prime, where phi of x is basically that long vector of an s of x for all different s's times lambda to the s over 2. Right? You can see that with these feature vectors you get an inner product. And then you resort to hashing, so you use this idea up here to compute this efficiently. And this works quite amazingly well. Okay. So lots of people have tried to come up with a lot smarter algorithms, and yeah, we did that too. And so you can do suffix trees and suffix arrays and compress things and prove a lot of nice things about data structures on strings. Unfortunately, they all very quickly run out of steam as soon as you have a real size data set, so don't use them. Use hash kernels if you don't care specifically about which attributes are extracted. If you do care about which attributes are extracted, you should talk to this gentleman over there. So Mu Li, he and Li Xu just submitted a very nice paper to KDD, which has an alternative data structure. Who does that? Okay. So this is, I think, all I wanted to say about hash kernels. And now we can move on from hash kernels to compressing entire matrices, and then we'll switch back to, you know, other randomized algorithms, how to compress matrices and what to do with them. Any questions so far? Yep.
I didn't really get how you solved the fact that you might be summing over a really few lists.
Oh, okay. Yes. So first of all, the sum only goes over the substrings that are non-zero. So therefore, okay, suppose I have a string of length L, and I want to do something with it. Okay, so this is X, and it goes from position 1 to position L. Now, if I was to consider only unigrams, basically single characters, I would have a cost of, there are only, you know, L positions that I need to look at. For bigrams, I'll need to look at L minus 1 positions, right? For trigrams, at L minus 2, and so on. So worst case, it's going to be L times L plus 1 over 2. So worst case, you know, generating all pairwise sequences, well, all sequences with arbitrary length is going to be a quadratic cost in the length of the sequence. In practice, well, there's a limit to which this is useful, because you can, for instance, assume that, you know, in text or whatever, you might not have that much coherence beyond maybe 5 or 10 words. So therefore, the algorithm is not going to be more than, you know, order length of the document times 10, for instance. So that's how you can very quickly generate all of those. Now, if you need to worry about wildcards and substrings, it gets a little bit more expensive, because you need to substitute each possible location with a wildcard and hash that up. But what you notice is that now the cost is only, you know, exponential in the length, it's only quadratic in the length of the sequence, and again linear in the exponential in the number of wildcards that you can place, because you could have one here and one there, but no longer dependent on the alphabet size. It's not such a huge deal in bioinformatics. It only buys you, you know, 4 to a suitable power. But in documents, when you have, you know, 30 different characters, well, 30 to the third, 30 to the fourth is a big enough number that you will really care. But yes, you want to be reasonably effective in generating those substrings.
So again, like, it seems like in some of your examples,
Mm-hmm.
K of x, x prime, your x's are documents.
Correct.
Some other ones, your x's are just single strings. So it seems like spam filtering you want to do for single strings, but for other document matching or something, you want to do entire documents. So what,
Correct.
typically, what is K of x, x prime?
Okay. Okay. So first of all, you've nailed exactly the point, namely it depends. Okay, that's probably not the answer you wanted to hear. So for bioinformatics sequences, you basically treat things as one gigantic long string, and that's that. And you basically have some maximum length of maybe 100 or so, because beyond 100, it's quite reasonable to assume that there aren't many coherences beyond that. Probably somebody who does bioinformatics for a living will tell me that I'm wrong, but turns out that this is not a bad number. Now, for documents, if you can assume that there is no real malice in how the documents are being generated. So in other words, you don't have the V1 agra kind of problem. Probably substring, bigrams or generally n-grams are a good idea. Sometimes people, however, do use things like stemming to deal with the fact that, maybe the same sentence in present and past tense, while it would not match at all, if I care about the tense, still means something very similar. And so with those things, you can, factor out certain parts that you can consider as being invariant relative to the thing that you want to predict. It's not always clear that stemming really helps more than it hurts. So this is something where really our friends in LTI would have a lot of practical experience. Every once in a while, as in every 5 to 10 years, somebody goes and writes one gigantic empirical paper of, here are all the 10 things that we tried, and these are the 3 that worked. So that's probably what I would recommend doing, as in read the paper, not necessarily write one of those. But it's very, very domain specific. And it may also be language specific. So for instance, for Asian languages, you may very well care about individual characters because they essentially map to entire words, or pairs of characters might map to a word, depending on the language. So for instance, in Korean, you can treat it pretty much as phonetic. If you use Chinese, then yeah, basically a character can be a word. Yep. Any other questions?
Is there also tree kernels?
Oh, okay, yes. So there are plenty of tree kernels. So there are plenty of kernels on trees and more generally on graphs. So for instance, one application that we used hash kernels for, this was actually one of the motivating drivers for us to come up with this idea, is when you want to compare graphs, one way of comparing them is by looking at all small subgraphs that you generate in a certain way, and then actually keeping a dictionary of all those subgraphs is kind of painful. So there's something called graphlets, and essentially the idea there is you go and extract all those subgraphs from the full graph. You thereby generate the full feature vector, and then you can, classify as you wish. Likewise for trees, you can, for instance, look at tree fragments and so on and compare accordingly. Not all of those kernels map very cleanly into hash kernel. They don't all. So in some cases, you can actually come up with other very effective, sometimes randomized strategies. So there's, for instance, something called the Feistel-Network kernel, and we might actually talk about that a little bit later. But basically, in settings where you have a vast feature set, you don't quite know which one matters, and you don't care particularly much about the coefficients, hash kernels are good. If you care about the coefficients, then you should use cuckoo hashing instead, and you'll be able to get, at a modest overhead relative to hash kernels, exact feature attributes. So, because basically with this, we don't store any of the signatures of the keys. So basically, this is terrible for L1, or group sparsity, or lasso, or anything of that form. Okay. Any other questions in this context? Okay. Good. Then let's just swiftly move on. So there's a paper that we wrote. It was called Coffee Rank, and you can roughly imagine what happened before we wrote this paper. We had way too much coffee. But actually collaborative filtering. So let's say I want to recommend things to you from Amazon. And Amazon has this insane inventory of things. Let's say they maybe have 1 million products. And, well, Amazon might want to have maybe 1 billion users at some point. And if we do this, then even just for the 1 billion users, storing all the factors is painful, right? Because that's, even if I just assume that I have 100 factors, then this is 800 gigabytes. And, well, those machines are still very expensive to get. Okay. So what you can then do is you can write a beautiful systems paper about how you distribute this and solve it in a distributed fashion. And you can send that to a systems conference, and that's a fun thing in its own right. Or you can say, well, let's make that problem go away by simply compressing the matrix. And the rationale is, in a way, the following. So among this 1 billion users, well, not all of them really come back that frequently. So there's a lot of users who, you really wouldn't need to do a lot of personalization for, or maybe they show up and at some point they go away and you really don't need to personalize much for them later on. But basically, it's quite conceivable that this is way too much storage for all those users. So you basically want to have a mechanism by which you allocate storage such that you can get collisions, but where those collisions essentially, don't make you pay so much. So we want to have something where it fits all into main memory, and we want to be able to have an instant response for each user. Why would you care about this? Because otherwise you have to fetch it from disk. By now, this is a bit more of a moot point, because with a solid-state drive, you can quite conceivably pull a user parameter from disk before the user actually gets an answer. Because you can do that within, single milliseconds. So within a millisecond you can get this, and users will not, start to notice a lot of problems if your entire system response comes within 50 to 100 milliseconds. Beyond that, people notice, and you can actually do measurements and see that you make less money on sales and ads if your server response is slower. So, yeah. But basically, this was the original motivation, and when we wrote this paper, SSDs were still like crazy expensive. The other thing that why you might want to care about this is privacy, because, well, what if somebody goes and actually leaks parts of the parameter vector? Can I do anything with it? So let's just recall the hash kernel. So we have this simple construction. And here's now what I'm going to do for collaborative filtering. So, okay, who has seen collaborative filtering before? Okay, good, great. So here's what you usually do, right? So you have basically some user vector U, and you have some movie vector V. And what you do is you basically have some recommendation Rij, which is going to be similar to maybe Ui transposed Vj. Conveniently, usually we have a normal distribution of this, and then maybe have some noise. And I'm skipping biases here, but basically that's the costly term here. So this is sort of, in a nutshell, the basic structure of a lot of those Netflix models. And then you can go really crazy fancy in terms of what you do in terms of time and so on. Now, as you can immediately see, if I have my ratings matrix R, that even this matrix here still uses a lot of memory. So let's say this is users and this movies. Storing this is expensive. Now, what we then did is we said, well, hey, since we found out that hash kernels work really well for vectors, can we use it to compress matrices? So, in other words, we used the construction that I basically have U sub I is, so basically little u is basically hash of capital U, which is basically the hashed version, and let's just walk through the various terms. And you can see this is exactly what the count sketch does, right? So this is basically, treat the matrix U as a data stream where I have keys of the coordinates, let's say j and k, with a value u, j, k. Okay. So now what I do is I add the value ujk to the bin I for which hash of j and k equals I. But I multiply it with some, Rademacher hash sigma of j and k. Actually, it's called psi, but this was called sigma before. Okay. And you do that for not just the users, but also for the movies. Or maybe you only do it for the users, because for the movies, maybe you can actually afford storing this matrix explicitly. Okay. So now what obviously is going to happen is that, those vectors for different users are going to collide. Okay. But then you can easily, instantiate an estimate of xij. So this is basically this rating matrix here, by just, retrieving elements from u and v. So little u and little v are the compressed representations, multiplied with the corresponding random signs. Okay. Now, what you can actually show is, first of all, and this is very easy to do, by taking expectations of xij, taking expectations with respect to sigma, you'll see that the inner product is preserved in expectation. Furthermore, you can show also by then looking at the variance that the variance is basically the Frobenius norm of the matrices U or V, respectively, divided by number of bins. So that's also fairly straightforward. So what you therefore get is an estimator where the expectation is great, and where the variance goes like, number of 1 over number of storage units. So if I give you more memory, your approximation is going to get better. And yeah, just to go through this, you can basically compute terms accordingly. Okay. Now, can somebody see a really big problem with this approach on real hardware? Okay. Let me give you a hint. So if I do collaborative filtering with conventional matrices, well, what I would do is I would, for instance, have a matrix for the users. And all the attributes for a user would be in sequence. And have the movies, and I'd also store it accordingly, maybe here. And then when I take an inner product, I would go and iterate over those pairs, right? I have one pointer each, and I then just move forward here in this direction. Right. So this is what happens with run-of-the-mill collaborative filtering. Now, what could possibly go wrong if I use the hash kernel? If I use hashing for collaborative filtering? So remember, the locations where I can find this vector here are now no longer sequential, but they're all over the memory. And so when I compute this inner product, I might end up picking, let's say, one pair here. Then maybe another pair there. Maybe another pair there. Okay. Why is this bad? Exactly. Because those things are huge, right? I mean, these are at least 1 gigabyte. Quite possibly a lot larger than that. So in other words, what I've now done is I've just traded off memory footprint efficiency with a absolutely disastrous cache miss, guaranteed cache miss at every step. Right. Well, So can you localize things? Well, as a matter of fact, that's the solution to the problem. Because, see, here's the issue. If I have hash of I and j, okay, so as a matter of fact, what we are afterwards going to see is that one suitable approach is to define this as hash 1 of I plus hash 2 of j mod n. This actually turns out to be not a totally unreasonable thing to do, and we'll prove afterwards that this is actually two ways independent if these two different hash functions are also two ways independent. So you could basically construct it from a single four ways independent hash function. You can construct this with suitable stuffing of arguments. Okay. So what this basically means is, you know, in our memory array, pick an offset. So let's say this is hash 1 of I, and then jump around relative to this offset. Okay. So there's a naive and obvious fix that you could use. And the naive and obvious fix is, well, let's just make h2 really small. Right? But this is a problem because of the birthday paradox. Because let's say j ranges of the values from, let's say, 1 to 100. In this case, that thing here needs to be in the range of 10 to the 4. Otherwise, I'm immediately guaranteed that systematically some coordinates will collide, so I'm automatically guaranteed to lose some information. Okay. Furthermore, you know, for two different strings where, you know, I go and collide at one point, everything else is bad later on. So how can you fix this? So we clearly don't want self-collisions here in h2 of j, but we like the fact that there's a bounded range. Does somebody have an idea of how I can get a permutation in that range that guarantees, well, how I can basically generate a permutation rather than just a random hash, and do that in comparable time? Okay. Any idea? Okay. Well, the solution is to encrypt things. So you basically use a cryptographic hash. Well, okay, not quite cryptographic hash in the cryptographic sense, but basically here's what happens. If I have a document that's 1 kilobyte of length and I encrypt it, there are encryptions that will generate another now garbled document of also 1 kilobyte of length. As a matter of fact, if I don't pad things to some fixed length, I can use this as an attack to find out what's in the document. But basically, there are encryption algorithms which give me a one-to-one mapping from n numbers to n numbers. And if that mapping is essentially random, I have a random permutation. More specifically, there's actually some construction that's very, very easy, and I should probably briefly mention that. It's called a Feistel network. And probably people here will call it a Feistel network, but the EI is definitely I in German. And it basically proceeds as follows. So this is for encryption. I have a function f of x and y, which is going to be y, and then x XOR hash of y. Okay. So if I do this, then immediately, as you can see, this is a one-to-one mapping between x and y and this pair here. Because for y you have the identity, so this is trivial. And for x you have the XOR with something that doesn't depend on x. So this is fine. Now what you do is, if you perform this at least 3 times, so you perform f, concatenate f, concatenate f, you actually get a cryptographic hash. You get an encryption of the X and Y pair. And to invert it is also, of course, very easy, because if I have Y, then I can figure out what X was based on this value, and you just peel back one layer after the other. I'm not interested in decrypting things here. However, what this does is it will give me an offset that is such that there are no collisions. So I'm basically going to use the offset plus an encryption in a range little n, so this is here capital N, of, sorry, this should be an I of j conditioned on I. So this way I can avoid that, if things just are shifted by 1, I get a lot of systemic collisions, so I'm going to get a different encryption at each point. And now I have basically two knobs that I can play with. Memory inefficiency, that's basically based on this range, and basically, how much collision I want to tolerate. Okay. Good. So this is essentially what you can do in terms of compressing matrices and making things memory efficient and so on. Yeah, by the way, yes, you can use this then for collaborative hashing. You still need to combine this with various optimization algorithms, and yeah, maybe Subrit is going to cover some of these factorization algorithms. So, and yeah, it does something reasonably useful. So basically, what you can see is that, the more memory you allocate, the better things get. So red is good, white is not so good. And so you basically get the effect that, the more you can compress, of course, the worse your recommendation performance gets, but it's not catastrophic, and at least now you have a continuous parameter where you can tune, well, okay, maybe you give me more memory, and I'll give you a better estimate. There's a lot more material that you might want to look through, and yeah, the slides will be up online. You can basically look through a lot more things there in the context of sketches and so on. Okay. Any questions so far? Okay, good. No questions? Everything clear?
Why does that have to be 3 conditions?
Because for, okay, so 2 might already do, but for 3 it's basically strong enough that you can't easily invert it. So basically, the more often you scramble, the harder it gets to work your way back. And so for the proof to go through, you need at least 3. So the place where to look for is, it's called a pseudo-random permutation generator. And this is also useful, for instance, if you need to generate permutations over a large set of elements, and you don't want to do the, well, let me generate random numbers in MATLAB, then sort them, and basically use the index of the sorting to get a permutation. I mean, that's like the cheapest 2-liner how you can get a random permutation. You can use encryption to get another pseudo-random set of permutations, and this way you don't need the full mapping of the permutation in order to know where a particular element goes. Okay, so that's essentially where this is coming from. So search on Wikipedia for pseudo-random permutation generator. So sometimes abbreviated as PRPG. Okay. Any other questions here? So there's a lot more detail on one of my blog posts on that entire issue of offsets, encryptions, and so on. Okay, good. So then, now let's first of all shut the system off. And I need a bit of enlightenment. Thanks. So what we're going to do now is switch back to, well, basically reusing the count min sketch directly or the count sketch. And we're going to use, I'm going to cover now something from a paper that's called compressed matrix multiplication. This is by Pagh, so P-A-G-H, and it appeared, I think, last year in the ACM Transactions on Computational Theory. So it's a good journal, and it's a very good paper. So the idea is going to be the following, and I'll give you that as a hint before we go into details. My goal is to multiply two matrices. Let's say A times B transposed equals, you know, some matrix M. And I want to be able to approximately solve this product without necessarily having to do really the cubic time operations that this involves. So I'm assuming that A is in 1 times K. This is in 2 times K. So basically, this is N1 times N2. And the usual operations would be, of count would be N1 times N2 times K. So the question is, can I do this more cheaply? How cheaply can I do it? Are there specific algorithms that I can use when I know that M is going to have only non-negative entries? Can I do it very cheaply if there's only a small number of non-zero entries? So these are essentially the types of questions that you would like to answer given this product. And without giving too much away yet, the idea that Pagh had was to compute a sketch of this matrix M efficiently, and then just query that sketch. And the sketch that he actually talks about in this paper is the count sketch, which works for general matrices, and for reasons that are completely inexplicable to me, he didn't even discuss count min sketches and so on. And there are a lot of nice reconstruction theorems, so it's just that these are all too small divs to actually bother writing them up separately. So this is basically, yeah, just stuff that I made up after reading that paper. Okay, so I'm going to show you how this all works. Basically, if I had the sketch of M, and I'm going to use exactly the same representation that we used for collaborative filtering. So the difference is we compress the factors such that we can, you know, compute the product in a more memory efficient way, and also, you know, learn the factors. He goes and compresses the end result and does that efficiently. So that's the key difference between what we used it for collaborative filtering, and what he uses it for fast matrix multiplication. But the technique is effectively the same. So what I basically have is, you know, S of entry I and hash of, you know, J K index I, you know, goes plus equals sigma sub I of J and K M J K, and you do that, yeah, you do that for all I in 1 up to D. And obviously this matrix here is now going to be in R, you know, N by D. Okay, so this is really just using the count min sketch or the count sketch for representing that matrix. And the entire trick is going to be how to compute this thing without really having to compute the product first and then compressing it. So is everybody cool with the problem that we're solving? Because it'll take us a little bit of work until we get to the algorithm that actually solves this. But the motivation is basically I want to be able to compute the product cheaply, approximately, possibly find the really large entries very fast, and I want to have good guarantees for it. Okay, good. So that's our goal. And by the way, whenever the retrieval is of course going to be m hat jk is going to be the median of s over all i's of s of I hash I of j and k times sigma I of j and k. Right. So this is the same thing as what we had before. And if we had non-negative entries, we could get rid of this term here, this Rademacher hash. And this would turn into a min over j. So that's the key difference between non-negative entries and otherwise. Okay, good. So the first thing to go through is the fact that convolutions can be computed rapidly through the fast Fourier transform. Who thinks you know this well enough that you could explain it on the whiteboard? Some hands should go up. Okay, so probably I should explain it then, right? So who has an electrical engineering background? Okay, you guys should know it. Signals and Systems 101, right? Okay, anyway, I'll explain it. So this is basically just deriving Fourier transforms and convolutions on vectors as opposed to on functions. And yeah, because we only have it for this. So I'm going to define A convolved with B. Index I is going to be the sum over all j going from 1 to n, so assuming that they're both n vectors of aj b of I minus j mod n. Okay. Trick question, why do I need the mod? Exactly. I need to, it could be smaller than j, or, yeah, that's effectively all that can happen. So you basically need to map it back into that vector. So I'm not really looking at vectors, I'm actually looking at rings. Speaking of which, this paper, when you read it, the first page is engineered to be as ununderstandable as possible by expressing that entire cool result as a statement about rings on polynomials. And it takes a while to decode it. But there's a very nice connection to them. Yeah. But we are not going to bother about them here. So if you like this, read this paper after the class and the paper will make a lot more sense. It's beautifully written once you understand what he meant to say. Okay, good. So we probably all still recall, the continuous version, and there it was just, integral f of x, g of tau minus x dx. That was the integral. That was basically f convolved g evaluated at tau. Right. So the first thing to remember is that by symmetry, A convolved with B equals B convolved with A. And the way to see this is simply to reindex things, right? So you reindex this as some variable, let's call it k. From that, it follows that, you know, basically now you have j. Well, if we have I minus j equals k, then, of course, we have that I equals, well, k minus j, well, sorry, j equals k minus I minus k, and then you plug those in, you reindex here the summation, knowing that you can go around anyway as long as you touch each element once, and by that you can prove that A convolved B equals B convolved A. Basically, you can think of it as the overlap between two functions, and you basically measure how similar they are there. Okay, good. So the next thing to look at is the Fourier transform, and the key tool that will actually let us compute this efficiently is the fast Fourier transform. So what we're going to exploit is the fact that for convolutions, you can compute them rapidly by convolving the argument, by Fourier transforming the arguments, performing a pointwise multiplication, and then applying the inverse Fourier transform. So what we will be able to do is that we will be able to compute A convolved B cheaply by performing an inverse Fourier transform of the Fourier transform of A pointwise multiplied with the Fourier transform of B. And don't worry, I'm going to derive this. So the only thing that I'm not going to prove is that the Fourier transform and its inverse are really, you know, inverses of each other. So with Fourier transforms, the one thing you need to be careful about is how they write out their normalization, because, you know, sometimes you're on R, sometimes you're in an interval, sometimes you have a finite number of elements, and then people conveniently sometimes put all the normalization into the forwards or all into the backwards, and some people put it in even proportions into each of them. So just be careful with this. So to avoid carrying around too many indices, I'm going to define it as follows. So AK is the unnormalized version, so it's basically j equals 1 to n aj e to the minus 2 pi I, so this is the imaginary number, j k over n. And furthermore, the inverse transform is sum over j equals 1 to n, 1 over n aj e to the 2 pi I j k over n. Okay. So this is just the Fourier transform and the inverse Fourier transform. So basically this is defined as f of lowercase a. This is defined as the inverse Fourier transform of A. And as you can already see, this is the inverse of that. And if I had gone and actually used 1 over square root n on both ends, I could see that this is then an isometry. In other words, lengths of vectors and therefore also in the products are the same in both cases. So in other words, this is a very special rotation matrix. Okay, but we're not going to bother about this here. So I'm going to quickly show the convolution theorem, so the one that's just now hiding here. And let's just actually go and compute the Fourier transform of the convolution. I really just need only one very long line. F of A convolved with B index L is sum over j going from 1 to n. So this is going to be our Fourier transform part. So we have e to the minus 2 pi I j L over n. And now in here I need to plug in the definition of the convolution. So I have a sum over all the k's going from 1 to n a k b j minus k mod n. Now what I can do is I can rewrite this times, so I have here j minus k plus k, right? Nothing has changed, I've just subtracted and added k. Now, of course, this means that I can pull those factors in, and I'll basically now get, and since the sum also works, I can pull this in as well. So I basically get one sum here, j minus k, and I get the other term here. And so if you squint hard enough, you'll see that this is the Fourier transform of A, pointwise multiplied with the Fourier transform of B. And that's what I need to know. So this is the convolution and Fourier transform result. And then, yeah, the other thing that we need to know is that computing the Fourier transform can be done in n log n time with the usual divide and conquer trick. I guess everybody knows that. Otherwise, really look on Wikipedia for the fast Fourier transform, and in MATLAB it's just FFT, and it's actually reasonably fast. Okay. Any questions on this? This is really just background. It's useful to know anyway. And by the way, this is also how you multiply with banded diagonal matrices efficiently. These banded diagonal matrices are essentially glorified convolutions. Okay. Everything clear? Cool. So, next thing. Yeah. What I need now is to get a few properties for hash functions. Basically, I'm going to show that hash 1 of I plus hash 2 of j, and furthermore, sigma 1 of I times sigma 1 of j are two-ways independent hash functions if the original hash functions h1 and h2, likewise sigma 1 and sigma 2, were pairwise independent to begin with. So I'm only going to prove it for this case here. The rest is identical, really, so wouldn't be really worthwhile doing. And then, yeah, of course, mod n. There I don't need any mod because I'm in a different semi-ring. I am basically in the Boolean semi-ring of 1s and minus 1s. So, pairwise independent means that the probability over all hash functions that hash of x equals I and hash of x prime equals j, that this thing here equals 1 over n squared for x not equal to x prime, and furthermore for all I and j. So more specifically, they could be the same. So this is pairwise independence. And that's actually all we need for the count sketch and the count min sketch, so therefore that's what I'm using. So the other thing that I'm assuming is now that, of course, H1 and H2 are independent of each other, but also that, no, H1 is pairwise independent in its own right and H2 is pairwise independent. One way of getting this, for instance, is to take a full ways independent hash function, carry it with an additional argument, namely 1 or 2 in this case, and then, of course, it works. Okay. Now, obviously, if I want to produce a collision, right? So the probability over all hash functions, so that's hash 1 and hash 2, of basically hash of I and j equals x1, x2 equals I, and furthermore hash of x prime at 1, x prime 2 equals j. Well, that equals the probability that for all these hash functions h1 and h2, that h1 of x1 equals, okay, a, and h2 x2 equals b, such that a plus b mod n equals I, and then I get the same thing here for the primed quantities. So basically x1 prime, a prime, b prime, x2 prime. Okay, good. And now all we have to do is just count things, right? Because now I have 4 different numbers. Chances that, you know, any specific combination of those 4 different numbers occurs is 1 over n to the 4. Okay. For any choice of a, b, a prime, and b prime. However, I have n squared many of those opportunities to make this happen because I need to get this to match up and I need to get that to match up. So I basically now have times n squared, which now gives me exactly 1 over n squared, and I'm done. That's it. So what you can see is that these hash functions are well behaved. Okay. You can make the same argument for the binary case, and what you'd get is basically n equals 2. So okay, you'd basically get, you know, the probability is a quarter. This makes things rather easy later on because we're going to use these very special hash functions to compute this. That's what we're going to do next. Any questions about it so far? No questions? Everything clear? Oh. Okay. Good. So, actually, let me use the other slide over there on the left because that's a little bit more readable. So I think we can get through the basic idea of how it works. Okay, so let's actually write out M equals A times B transposed. Okay, so this is nothing else than the sum over J equals 1 to K of AJ times BJ transposed. So basically, if this is a rank K matrix, I just have the corresponding row and column vectors here, and I compute this. So the approach is going to be now to compute sketch of M as the sum j equals 1 to k of sketch of AJ times BJ transposed, which initially looks like a crazy stupid way of going about things, right? So this is like I'm going to compute sketches of rank 1 matrices, which are really wasteful representations, and then I'm going to add them up, and the claim is that this is going to be faster. Okay. Now it turns out that this thing here can be written as follows. So I'm just going to drop these indices j now, because otherwise it just gets super painful. So I'm actually interested in the value for a particular bin. So S of A, B, indexed by L, so that's bin L, is the sum over all i's and j's with a property that hash of I plus hash of j equals L mod n. Okay, that's the condition, because we need that they match up, otherwise they won't fall into this bin. And then we have sigma of 1 of I times sigma 2 of j times AI times bj. Okay. Right? Because this is, this rank 1 matrix read off at position ij. That's that's sigma of ij. That's exactly what we proved before on the right. And this is hash of ij matching into bin L. We just proved before that this is okay. L is just, S is a sketch of length n. Goes from 1 to n. And L is some position. That's basically the Lth bin. So this is the same thing as what we had in the count min sketch before. I'm just, I need to index it, because then the algebra becomes a little bit easier to parse. Okay, this is all in the eye of the beholder, right? Now, if you look at this, this is basically nothing else than, the sum. We can now pull those sums out. It's basically the sum over I, sigma 1 of I AI, sum over j, sigma 2 of j bj, under the condition hash 1 of I plus hash 2 of j equals L. So now let's, for a moment, consider compressed vectors A and B, where I'm now applying the same count sketch to A and B respectively. So this is nothing else than sketch of A convolved with sketch of B indexed at position L. Because the only place where I'm letting things collide is given by hash of I and hash of j respectively, and they have to sum up to L. This is exactly what we had before there, where we defined a convolution right up on top. Okay, so now this is awesome, right? What we just proved is that sketch of A times B transposed equals sketch is the convolution of the sketches for A and B. And so now I can just apply the Fourier transform theorem, and I get that this is nothing else than the inverse Fourier transform of the Fourier transform of this object, which is of course nothing else than the Fourier transform of this, pointwise multiplied with the Fourier transform of that, pointwise multiplied. Okay. So now all we're going to do before ending the class today is just do an op count here. So computing this thing here is going to cost order n1. This costs order n2 operations. Doing the Fourier transform is going to cost n log n. Likewise here, n log n. I mean, it's actually a sparse vector, but you can't do much better in terms of the Fourier transform. The Fourier transform actually acts as a densifier anyway. Pointwise multiplication of those two things is order n. And then the inverse Fourier transform is another n log n. So the total budget is order n log n plus n1 plus n2. Now, we need to do this k times, right? So n is the size of the sketch, right? So now I'm going to multiply this by k. And that's it. So this number can be a lot nicer than that number up here. Basically what's happened is that rather than having a three-ways, basically a trilinear dependence on n1, n2, and k, we now only have bilinear dependencies on these. And then a dependence on, well, basically how precisely we would like to have the answer. So as a matter of fact, okay, actually there's another term here, right? There's basically this d or b, which is basically, you know, the probabilistic guarantee. So in other words, what we'll really afterwards get is log delta, log 1 over delta. And this is going to be 1 over epsilon log 1 over epsilon. Okay. That's going to be the cost in order to compute with probability at least 1 minus delta the entries with accuracy of log epsilon. Actually, I cheated a little bit because I would really have to put here n1 plus n2, n1 times n2 over delta, because what I really have to, well, sorry, no. I'd have to do 1 over, yeah, that's okay, yeah, n1 times n2. Because if I want to have my guarantees to hold uniformly, I need to pay this. But that's now the cost for performing approximate matrix multiplication by using fast Fourier transform. Okay. The one thing that I haven't told you yet is that this entire reasoning goes through for tensors. And that crucially relies on the fact that if I have A convolved B convolved C, for instance, this can also be written, if I Fourier transform it, as the product, as basically Fourier transform of A times Fourier transform of B times Fourier transform of C. And obviously for higher order tensors this also works. Secondly, I can also show that if I have non-negative entries, I can use a count min sketch rather than the count sketch. And the only difference is that wherever you see sigma here, you just get rid of it. And wherever you see a median, you turn it into a min, and problem solved. This is very straightforward. For reasons that are really unclear to me, it's not even mentioned in this paper. We'll get into a few more of those things later on. So I think we've reached the end of today, and we'll get kicked out probably in a minute if I don't finish. So any questions while I pack up?
Do you have a one-page write-up?
There is. I don't think there is an easy one-page write-up, but I will make my 3 gigantic page write-up available as a scan. Secondly, there's an 18-page write-up by Pach. But yeah, it takes. So my guess is the key idea of the entire proof is really this bit here, right? That's the key bit. That's really the key novelty. Everything else exists. Yeah. Correct. So, okay. So the accuracy is epsilon. Well, so So what I hid here is that actually there's the Frobenius norm of the matrix showing up somewhere, but I think I'm being kicked out. Yeah, guys, come in. Don't worry. So this is the one thing that I hid.